Buen día a todos. Good morning.
Buen día.
Hoy, vamos a tener la presentación del doctor Claudio de Ciccio. Claudio, es un placer que esté aquí, realmente. Estamos muy agradecidos, porque además ha sido siempre muy amable con nosotros, que lo conocemos hace no tanto tiempo. Claudio hasta diciembre, creo que lo comenté el martes, hasta diciembre trabajaba, adelante, en la Universidad de Sapienza, en Roma, y desde diciembre está en la Universidad de Utrecht, en un grupo de investigación muy fuerte en BPM y minería de procesos. Así que, no sé, nos va a sorprender con cosas mágicas, seguramente hoy.
No,
Así que adelante, Claudio, muchísimas gracias.
Thank you so much for introduction. As said, sorry, I'm switching to English, and yeah. So indeed, I now work with the group of process science in the Utrecht University. Indeed, it was so strong that they said, well, we have to hire someone to, lower the level overall, and that's why I ended up there. So, right, so there is a Faculty of Science Software Division Process Science Group. It's recently rebranded as such. So, what are my main research interests? Well, okay, process mining. So far, so good, yeah? But typically what my field where I come from is about formal methods, logic and computation, automated reasoning. So this kind of, the boring part of AI, essentially. And right, and I apply these techniques, we really enjoy applying these techniques into two domains. The first being process analytics, and also more recently since 2017-18 to blockchain architectures, but that's another story. Right, so this is basically my story so far. So I've started in this very ugly building here, which is now devoted to a mall. It's a shopping center, and it's good that it's so, because once it was even raining in the room in which I was taking the exam. That was terrible. Can you imagine during the original test, while this drop after drop next to you, at some stage, there you go, right? But then, yeah, of course, now they moved to a more fancier place. Then I moved to another even fancier place in Rome with a cloister and all that. Then went to Vienna for my postdoc first, an assistant professorship later on. There I worked with Jan Mendling. He's another superstar among the many we have seen thus far. So can you imagine, like, I've been working with Hayo Ryers and Jan Mendling. They're two of the four authors of the BPM book, the Bible, right? So, and also Marlon is around here. So, well, quite a group. And okay, so then after 7 years in Vienna, I moved back to Italy, but that's interesting because it was another department. So I am by training an engineer, but I became an assistant professor and then associate professor in the computer science department. They're two different things. I know it sounds strange, but there is computer science engineering and computer science out there. Now I can declare happy myself an engineer because I'm in Utrecht University in the Netherlands. So let's, I think it's, I've already been banging on useless details enough. Let's begin with this, okay? Let's keep this in mind. For the full for the full collection of hours, you will be forced to hear me. I'm sorry for you, but then this is a concept will recur again and again and again. So let's look at this picture here. And now I won't ask you if you think it's half full or half empty. I won't say that. Why is that? Well, not because of course it's full empty, right? We all agree. But also because in our perspective, rather than looking at this very photograph, we rather ask ourselves what happened the instant before and the instant after, right? So essentially, we look at the progression of events, so one after the other. And another tip, as if it was really, the film of a movie, we think in terms of discrete time, okay? So an instant, then another instant. It's not real time, which is kind of continuous, yeah? So keep this in mind. All right, so that being said, what we can declare, sorry, I switched too fast. We can declare that here the glass is half empty, and here it's the glass is being, the water is being poured off the glass, and here the glass is being filled in. So we're making statements in three different moments of the full history of events. You with me? All right, so let's proceed. If we can start considering reality in terms of this consecutive sequence of happenings, we can also start binding things that happen at a certain moment with things that should happen before, after, at the same time, somewhere, somewhen, sorry, wow, this is very elevated. An electrocardiogram must precede the prescription of a combination of medications. So you can't really prescribe medications that could affect your heart, your blood pressure or heart functionalities in case you don't have an electrocardiogram first, right? Which doesn't mean that everyone has to get some medicines, but in case we're prescribed, there should be this situation before, yeah? Okay, let's go more into our territory, right? A paper can be reviewed only if it was submitted before, right? So typically this is the idea. If you don't submit, you don't get a review. That's just pristine. So this kind of sentences state something that has to occur before an event happens, okay? So that's why they fall under the name of precedents. We talk about things that must precede, yeah? So we can also talk about things that should happen in the future. Response. If a paper is submitted, then the paper will be reviewed. Well, okay, I know, there is a desk reject, you're wrong. Okay, please don't take this literally. There are many errors in my in this specification, but nevertheless, just to give an idea, to have an idea. Let's say 90% of times, 95, if a paper is submitted, then the paper will be reviewed. Modulo, absence of PDFs, or I don't know, desk rejects and all that. This one is called response. Now you can see that if we fix the moment to right now, it's as if we're slicing time, discrete time, into what happens in the past and what happens in the future. Response prescribes what should happen later on, whereas presence tends to be something that you check now for what happened before. So far, so good? Okay. This again are the precedents, but what changes is the statements we make about the instance in time. So here we were talking about reviews and submissions. Here we're talking about acceptance and review. Okay, so we can't accept the paper if it wasn't reviewed before. Sure, it would be great to have also desk accept. I'd love it, but I'm not aware of it yet. I mean, maybe sometime. If you happen to have such an experience, please share, right? Okay, so then these are three constraints, or three rules, if you like. A set of constraints, or rules, if you like, is a so-called specification. Yeah? Dig it? Okay. So, among them, you might also find out there are some different prescriptions, such as not response. So, if a paper is rejected, it cannot be submitted afterwards. So, not, that's why not response. This is interesting. If an abstract is submitted, a paper was or will be written. That's the assumption, right? So, we're talking about things that could happen in the past or in the future, but at some stage it should happen. A bit sloppier. So I guess the logicians among you may already start thinking, hold on, there is a thing called subsumption. So if I state something that happens now and in the future, it's more restrictive than, yes, we'll get there. Okay, so if you, for the impatient, at some stage we also talk about the fact that these templates are not orthogonal. So one could imply the other. It can happen. That's the curse of redundancy, but take it or leave it. So what's going on there? While we were adding more constraints, one after the other, we were restricting the number of operations we can actually do. I repeat, if we add more rules, there are fewer things we can do, right? Okay, so imagine this pointy square is the universe of all possible behaviors, which is in proper English. So the possible behavior universe is this one, okay? It's a bit small, but okay. Then the process we are actually running, or we want to run, or we intend to run, or we discover is running, whatever, in fact is this guy here, okay? By process, I speak about behavior, basically, of the process. So I'm not talking about, human resources or mechanical resources, just actions, control flow, etc. Rules. Then we can also rename, please keep this name, this into account. All the executions that we run for discrete time creates sequences of events, right? Now, imagine just for a second, right? So we have the sequence of events. Then we say every event is a letter. A, B, C, or we can get to kanji if we like. Anything, right? So then the sequences are sequences of symbols. And a sequence of symbols is a word. What are all the possible words that our process can express? It's language. There we go. Keep this again into account. Again, there might be some logicians among you like thinking, language. So where are the finite state automata there? We'll get there. We'll get there. Okay? That's on purpose. So clearly, when we declare what we can do or we cannot do, well, we might be a bit imprecise. Yeah. So maybe we can't really capture every single little space here, but more or less, this is the declarative specification. Okay, we're trying to kind of define in a gross manner what are the things that go on. The more the constraints, the more we squeeze this area. Yeah. Now, we're typically more on Tuesday already, we said that, right? So when the process becomes more flexible, it might be a good idea not to say everything you can do, but rather say, well, there are certain rules you should really abide by, and the rest, well, it's up to you. Medical domain, for instance, yeah, healthcare. Why is that? Because the imperative model does the opposite. We start from a sunny day scenario, we call it, yeah, and then we start considering all the exceptions, all the possible, ways to overcome certain, problems, etc. So we start small, and if we add more transitions, more states or places, if you like, then it becomes, bigger and bigger. But the bigger it is, the more things you can do, typically, yeah, because there are more paths you can follow. Picture a Petri net, a workflow net, a BPMN diagram, an APC, whatever. So typically that's the idea. So they are really dual, right? So we start big. Again, logicians, fixed point operators. We start big, and we tend to restrict the space of possible behavior with declarative. We start small and we increase imperative. So they're basically complementary. They're two views. Now, to the extent that this is just a conjecture. It's not really proven as a fact. Yeah, but typically, more or less, rule of thumb, fewer rules, the fewer the rules, the more things you can do, so the more the paths you can have in your imperative process. Yeah? So I'm not sure if this is exact, but I can tell you I've not yet found anyone telling me, no, it's wrong. So more or less. This representation here, by the way, it's already using a graphical notation for declare, but these are kind of strange arrows with dots and all that. So we're declaring things about A, B, C, and D. That's the corresponding version with a workflow net. So we spoke already about the medical domain, but actually, if you think carefully through how we express in our society the norms are laws, and these laws or guidelines or regulations or ways of conduct or misconduct, they typically are not expressed like detailing your life from when you wake up to when you go to sleep, right? They don't tell you like you should actually stomp with your right foot because left foot typically means that you're a bit upset. People say, etc. No, but in the end, would it really matter if we're talking about the university regulation? I don't think so. Well, sometimes some professors could be affected by it, but that's another story. So typically we focus on what is really characterizing our domain, and we declare what happens, what should happen if certain things are done. And in most times when we talk about codex legal aspects, the structure is more or less the one you might be able to see it on the left-hand side. It's a bit small as a font, but just let me tell you. Typically, you have an infringement of a rule, and then what are the compensatory actions that should occur to repair for this infringement, right? So if infringement, then do. If, then it's a declaration of what's going on without dictating what happened before or after. We don't care. We just specify this. Yeah? Or even when it comes to driving. Now, it might be a bit puzzling because I took this picture while I was in Australia. So cars are not exactly where we expect them to be. But nevertheless, they just say, well, if there is a car coming from the right-hand side, well, left there. Anyway, so from the right-hand side, you should let it pass first. Yeah? They don't say, well, in your car, you should first enter, close the car door, then switch on the engine, then start, and then go, etc. No, they just say, well, if you happen to see a car to the right, just stop, because otherwise you're going to crash, yeah, and it's your fault. Okay? So this is the kind of mentality we have when we talk about declarative approaches to process specification. I'm shamelessly stealing this picture from the slides that Danielle showed before, which in turn were derived from a paper. But anyway, so basically, we're talking these particular specifications tend to be more apt for processes that go more or less to the loosely structured situation. I mean, if the process is completely unstructured, well, little we can say, little we can declare. So we typically stop here at the loosely structured situation. The conjecture, again, it's not proven as a theorem, but it's a conjecture, is that the higher the flexibility, the better is to focus just on the rules that basically tell you what not to do or what is expected from you to do without exactly dictating every single step. Did I get you hooked or convinced? Again, I tend to enjoy my voice, but please stop me, yeah, anytime. If you have questions, comments, remarks, damn! I know. It's a very ugly sentence, but I told you. At some stage, I mean, I'm one into the boring side of AI, so here we go. All right. So what also Danielle suggested was that declarative languages, especially the one we're talking about now, tend to have a strong, rooting into logics, formal logics, so as to give them some semantics that are given once and potentially forever, right? So it's less interpretable as a language. That's the idea. So now, I don't know how accustomed we are with this kind of strange glyphs, but okay, A means like the fact A, the proposition A is true in this instant, right now. Start is true only at the beginning of a sentence, of a sequence, and end only at the end of a sequence. So far, so good? Cool. Now, this is not to be taken for granted. So start, we can all imagine, but end means we are forced to consider all sequences to terminate at some stage. Okay? Why is that? Because this language here, LTL, was meant to depict semi-infinite systems. Say servers, hardware, yeah? Things that are supposed to start, switch on, and then stay on virtually forever, right? We instead using a restriction thereof, like imagining that all traces have an end. Again, I know it's gonna, I mean, from now to 1 hour and a half, we'll get back to this. So it's very hard that you remember in an hour and a half, but still try to say, well, remember when we talked about that? So we're talking about finite traces. So we have a start and an end. This kind of angle symbol is not. So not phi, where phi can be asked, a star, end, not. This triangle means and, comes from Latin, atque, yeah? So this means like phi1 and phi2 hold true in this instant. Vel stands for or. It's not either or, it's either or both. This is the trickiest one, implication. Hold on. Implication is strange, right? So remember, implication is not if and only if, it's just if one way. So if this guy is false, we don't care. It's always true. Okay? Cool. And then what the heck are these? Right, sorry. Circle. Circle is next. So if we just look at the first row, this is propositional logic. Good old, propositional logic. We've seen them in Carnot maps, whatever, computer hardware architectures, anywhere. Yeah, this is different. So this is basically taking propositions to the time dimension, discrete time dimension. Okay, we can take any propositional formula and project it into the future or the past. Yeah. So next instant, this is next. Clearly, you can see it from the shape, right? I don't know why. This is the lingo. Take it. I didn't invent it, so I don't take responsibility for it. So circle is next. Diamond is eventually in the future. Watch out. I know as an Italian, I know also in Spanish, eventualmente means, well, maybe. No, eventually in English means certainly, but sometime in the future. Okay, so sometime in the future. always now and in the future until so what's that? Come on, yesterday they call it. Yesterday, this guy, which means like the instant before, always before, and since, which is like until reversed. Now, of course, I don't expect to have learned it all by heart, so let's go by example. Yeah? Maybe it's a bit easier, perhaps. So let's look at this phrase. Now, typically, with propositional logic, we would say if A is true or not. Here, it's not enough. You have to say also when. Yeah? So semantics are a bit different. We say, given a certain instant, a step, does this hold true or not? So, A, does it hold true here? We expect a closed word assumption. So whatever is not written is false, okay? So, is it true here? No. But one moment after, yes, right? Nope, nope, yes, nope, right? There we go. So, given a sequence, we don't say if it's true or false. We just say, well, what? Hold on. At which instant are you looking now? This meant next. So in the staying here, I look at the next instant and check if A is true. See? No, no. See? No, sorry. No, yes, no, no. There we go. Right? So, guess what I'm going to ask now. Right? So, no, yes, no, yes, no, yes, no. Right? So, see, it's a game. A game we play a long time, but it's, in the end, only propositional logic. Eventually, in the future. This is a bit trickier. So, we have to look from now on. And if there is an A at some stage, then it's true. Okay, I'll just run to the interesting one. Right? So it's this, eventually A is always true until we get to this C guy. Notice also the current instance is included, okay? All good? The other way around. Right, so it's always true except here, because this B doesn't see any A before. Well, of course, there is no trace before it. One thing, for those of you who are already into automated reasoning, there is a easy trick to compute the pure past operators from the pure future operators, which is flip the sequence, the trace, right? So if we flip it, like reverse order, we can basically turn things upside down. This is easy. What's very hard is try to untangle the formula, because formulas can have an indefinite number of these guys that basically nest one another. That's a mess. But in principle, that can be done. In fact, we do. So process miners who do this typically take a trace. First, they pass it from the beginning to the end, and then from the end to the beginning. All right. Always B. I didn't take A because it would be too trivial. Always B. From now on. So, is it true? Why not? It's not always. Right, indeed, yes, exactly. So, no, it's not true here. Here it's B, but it's not always B. Right? Look, check the difference. This says as long as I have at least one A in the future, then I'm happy. Here it says, no, it has to be always B. So, no. Yes. Right? Flip it. Well, basically, this holds true only in one instant, which is the first. Right? These two are horribly difficult to explain, so so they work more or less like that. So A must be always true until B occurs, and B must occur at some stage. So why? B is true here, so I don't care about A. That's a trick. Ah, damn it! So, true. Here, why is it false here? because there is a B eventually in the future, but this is not A. This is A, and there is a B in the future, etc. Well, here it's always B, so we're good with that. Since it's just take the same trace, flip it, and you'll get this one. I have good news. We'll never use this 2 for the remainder of the lecture. This is just for your own knowledge.
Why the last A is not true?
You mean this one? Because it has to be always A until I see B. So here I don't see B and then I see A, therefore it's false. Also, it backtracks, reverberates. And it's already, I think, the 5th, 6th, 7th time that our colleagues told us, use this pointer, don't use your fingers. I'm constantly getting there with the finger. I'm sorry. I'm sorry. I tend to forget that. Sorry. Yeah, look. So here we had A, right? But in the next instant, we have C, not B nor A. That's why also in this instant, it's false. Oh God, what a... All right, keep this in mind. We'll get back to it in a few minutes. Well, more or less. So there is an implication. Maybe it's easier if I do this. Yeah, there is an implication here, and there is a next. So if B holds true here, then check the next instant and see if it's C. If B does not true here, I don't care. I'm so happy this is true. So, this is the result. Why? Let's look at this guy. This is B, right? This is B now. Is the next C? No. Meh. Therefore, where is it? A. This is A. Therefore, I don't care. This is not B, so whatever. I'm happy with that. B, and the next is C, so I'm happy with that. C is not B. A is not B. B is B, but the next one is A. Therefore, nope, etc. Yeah? Okay, this is basically, we finally come to one of our favorite constraints ever, response. If you submit your paper now, it will be eventually reviewed. Yeah? It is always true that if you submit your paper, then it will be eventually, well, more or less. In a mining context, it would say, well, 90% support, let's say, yeah, or confidence. With 90% of confidence, we can tell that it's always true that if you submit your paper, then it will be reviewed. Immediately, in the next instant, not even eventually. This chain response. So, basically, all of this violates the rule because it happens at some stage in the future that we have an A followed by a B, not by a C, right? Whereas from this guy on, it's always validated, right? So it's been a long exercise. I know it's kind of tiring, and I demand a lot of energies from you. Never mind. Now we'll go into things like Homer Simpson and all that. I'm serious. Well, almost. And yeah, but this is just to keep our mindset into this kind of particular realm. Things may be true or false depending on the instant you're evaluating them. Not always, unless you really write it down. Unless you really write, I have to take it. So, I should train a bit more on this. So unless you really write it down. So to state that something is always true, you have an operator to say that. Yep. Cool. All right. So this is a representation of all these constraints with a fantastic logic we have just used. You don't have to learn it by heart. Nobody cares less. Just saying, well, the good thing is that we see that if we use the same, if we use the same template, say response, the symbols we adopt are the same. What changes are the parameters, or actually the variables, right? So that's a trick. So we already see two levels of expression of the same constraint. So natural language, well, pseudo-natural language is more like pseudo-automatic, and formal. There's also graphical notation. Well, we'll get there soon. So at some stage, who determined these templates? Well, a pair of, no, actually, not a duo, but a triplet of scientists in software engineering. So in the seminal paper in 1999 at ICSE, they analyzed the most recurring templates that software engineers and developers would test their software with. So checking if the system does something now, what it's expected to do in the future, what it should have been done in the past, etc. So, and then they come up with a fantastic taxonomy of templates. Yeah. Then a few years later, and basically they made it such that they don't. And here I cling to what Danielle anticipated a couple of days ago. On purpose, the logics we use for these templates is not Turing complete. Why? Because we want to reason about it. You know, Turing complete languages are non-decidable. We just don't know. Given any formal specification written with a Turing complete language, there is no algorithm that can determine if they terminate or not. Okay? If you just give one instance, yes, of course you can. That's what we do every day. But if you don't know in advance, well, you can't really. In this case, instead, the decidability is still preserved. But you know, to make it preserved, then we have to reduce the things we can say, we can dictate. So to be more specific, hey, where are you? Oh no, to be more specific, if this is the circle of regular languages, so finite state automata, we are in a subset of it, a bit of it. And if you want to hear the big term, it's a free variable first order logic language. So we can express the full blown of LTLF with 3 variables in FOL. That's it. Okay. And this is indeed for the curious people. This taxonomy here represents the basically the same patterns on steroids. So they added a few more. We'll go through them in the next exercise. Never mind. And they tend to have this is-a relationship, right? So this is a, that is a, that. So it's extension. All right, let's go ahead. Now you'll see a few strange drawings and strange letters, if we can. But nevertheless, so what I'm sitting here, since now we have a language that is less expressive than another one, it means that the more expressive language can dictate everything about its smaller child. Yeah? I'll repeat. Imagine if you could talk about your life by never using the word bear. Right? So, well, I could talk about your life even if I used the word bear, right? So my language is more powerful, expressively powerful than yours, but still we can talk about the same things. Actually, I can talk about the things you talk about, but not the other way around. Yeah? So far so good? So, since LTLF is a strict subset of regular languages, then, bam, we can represent formulae in LTLF finite. Therefore, we can have an accepting state. If it was not finite, we wouldn't have accepting states. But we would have Bucci automata, etc. Well, never mind. So we have accepting states because we can finish at some stage. And trust me, yeah, so these are basically automata that can express exactly and only the language, remember? The language that models this particular formula. And the same occurs here, right? We don't have to learn it by heart, just saying, okay? So if you're familiar with automata or patronets, which are basically automata on steroids, this kind of sounds convincing, yeah? And now, something interesting. So now I'm talking in English. We might consider when you go to language schools, they tell you, well, if you want to talk in another language, try to think in that language. Don't think in your own one and then try to translate, because it's twice as slower. Indeed, that's exactly what I was doing now. Lento, right? So, however, we know that we can even be so cool to think in 2 languages at one time. That's what translators do most of the time. So, let's now reason with these 2 formulae. So there are 2 rules. The first one saying if you submit a paper, it will be reviewed at some stage, and if you submit an abstract, there also a paper is or will be or was written. Yeah? I said and. Why? Because a set of axioms make a theory. A set of constraints made of specification, they have to hold true all together. Now, if we think about, formal languages, the end comes natural, like it's and a, right, the triangle. What happens here? Can I make an automaton that is like comprising of both formulae at the same time? We can, indeed. An operation named cross product that you don't have to learn by heart, but just it tends to create now, uglier and uglier automata over time. So the cool thing is that basically we can reason at both levels, logical and automata based. All right? Keep this in mind. It will be extremely useful when we talk about discovery. Yeah? So, this is also a way to now prove formally that if we have few rules to the right-hand side, we have an outrageous mess to the left-hand side. Right? Few rules to the right, a mess to the left. Pretty straightforward. Okay, for the purists among you, when I use this particular symbol, which means equivalence, logic equivalence, I'm assuming that we're talking about the same alphabet. Yeah, so just saying, blah, 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 blah. So this is the same, so this is a third level of expression. We saw pseudo-natural language, formal language, also automata. This is the fourth one, which is like a graphical notation. There also is a graphical notation akin to, the wish, akin to BPMN or these other famous languages, or CMMN. There's a simpler one for declare that uses these kind of arrows. The modality is simple. If you see a dot, that's the if side. If you see an arrow, you're talking about the time. So, if submit abstract, then write new paper. Is there an arrow? No. Why? Because I don't tell if it's before or after. Here, if you submit the paper, then you send a confirmation email. When? Afterwards. That's why the arrow is like pointing outwards. Yeah? Look at this guy. If you accept the paper, then you must have reviewed the paper. So this is the kind of rationale. And then I don't absolutely know why the double cut means not. Why not a cross? Take it. Maybe because graphics didn't have crosses. I don't know. Anyway, so if you reject the paper, you cannot submit it again, right? Later on. Cool. This is instead what we will use today in the afternoon. The same, just on steroids. It's an application process for university programs. Yes. And let's go. So let's deep dive into templates. Again, we don't have to learn them all by heart. Our mission today is try to enter the lingo and the mindset, so that even if we encounter some new constraints we didn't remember, well, we can kind of guess. Okay, this might be about this and that. So,
Declare is a subset of LNT. Is a language. Is a graphical language. What is Declare?
Declare is a repertoire of templates. What does it mean? So it defines, well, there are debates about it, like 18, some say 24, some say 48 fixed templates, so you can declare the specification only using those templates, okay? And therefore, since it's a repertoire of templates, we can use it to specify languages. Which languages? Process traces, process sequences, process traces, yes, indeed. Finite traces. Okay, so I don't know how small the font is for you, especially in the back, but this is written here. You see init. So this is init. What does init mean? Initialize. So the very first event must be A. End is the opposite, right? So the last event must be A in this case. Then we have participation and at most one. Participation is also known as at least one. At least one means you have to find in the whole trace at least once an A. At most one, let me surprise you, means the opposite. Like you must find at most one. So 0 or 1. 2, not good. So these guys are called existence constraints because they dictate if and when one statement, an activity if you like, occurs. Just one at a time. But we said, well, if you submit an abstract, then a paper, blah, blah, blah. So there are two variables involved. That's why they're called relation constraints. Relation constraints tend to go through a strictness hierarchy. The loosest, with two O's, is this guy. It just says, if A, then B. When? Well, I don't care. Sometime. Past, future, I don't mind. If you say when, and it's in the future, then it's response. If A, then B in the future. And here comes what some people might call semantic perversion. So, using double arrows with double signs was not, unless they're actually the lines with which you draw your line. This double means alternate. And what does alternate mean? Well, it means that if you do A now, you must not repeat A until you see B. It's sort of, gating. A now, good. Then never A until you meet B. Then you can do A again. Why? Well, hold on. It tends to be very cozy. Unfortunately, it's one lecture today, or luckily for you. But if we talk about the translation from BPMN or other procedural languages that have these particular patterns named as, XOR branches, when we branch out and we join again, this is a perfect constraint to represent the same thing, because you have like A before this like a bunch of this fragment of the process, then you close with B and you can restart if there is a loop. That's basically why we use it for, to express something similar. Not the same, but similar. Chain response means instead, and this is why we have the Adidas, the tribal stripe here, means that not just eventually in the future, it means like the next instant. Remember the circle? That one, right? Cool. Now, it won't surprise you, but we said, well, actually, all the future operators have a dual past operator. So if we can talk about the future, we can also talk about the yay. Everything reversed. Response, you flip it, it becomes precedence, alternate response, alternate precedence, chain, etc. The not are also there, so not response existence. You might notice that here there is no not alternate, and the reason is really cool. Why is there no not alternate response or precedence? Because nobody has a clue what it means. Just simply like that. Nobody would use it, so why talking about it? It exists, it's there, but really we don't put it even in the what's that? Discovery algorithms. We just don't use it. Why? Because not alternate response, which means if I do A now, I must not do B, and while I do not do B, I also can't repeat A. What? That's why we basically don't use it. That's kind of, it's a sort of a glitch in the system, and therefore it's really not used. So we have the way forward, way back in the past, and if you were not satisfied with all this mess, there are also the mutual relations. Remember that we said, watch out, the arrow in the front is the if, but it can be an if and only if, right? If and only if. So if I submit an abstract now, I will get my paper reviewed. If I don't, fair enough, right? But also, if I receive a review, I must have submitted a paper before, otherwise there's something going wrong there, right? So you see, if now, then later, and if later, then previously. If and only if. So response and precedence together combined are called succession. Okay, you can see now that the shape is very very close to what we're used to. So there is the if, but the if is now on both sides. Look again. Ta-da! The if is on both sides. And to make things even more complicated, and I'll come back to you in a second. So we said forward, back, and there is the negation. But But since it's negation, we don't have not alternate succession because it would be even less understandable in general. So it's like, yeah, a distortion of our mind. Please.
Can you talk about activation and target in the...
Very good.
Explain a little bit what activation means.
Thank you a lot. So the logicians in the room may be aware of the two terms, which is antecedent and consequent, or premise and consequence, right? Just basically, if you have an implication, the if and then. So we can express this particular templates by talking about the if and the then part. So if is activation, and then is target. Excellent remark. So with the non-dual, so non-mutual, we have one if and one then. So that's why we have one activation and one target. Instead, when we use mutual relation constraints, and both sides, so both are activation and target. That's the idea. Thanks a lot. That was a great hook, because that also allows me to talk about discovery later on in a more detailed way. Thank you. Otherwise, I should have, come on, I forgot that. Thank you a lot, Jorge. Okay, great. So, as you can clearly see here, this is the monster that is running beneath a declarative specification, the one that we were talking about submission of papers and whatnot. Now, thus far, we've been talking about modeling variability, flexibility with constraints, modeling. So we are imposing what the process is, yeah? But when we do so, it can happen that we don't realize that among the various rules, there are loopholes. Now, think about it in our society. How many times it happens that we have new laws and we just go, oh, there was this loophole. That's exactly what's happening here. We give a full list of norms, and at some stage realize, oh yeah, right, there is this thing that can be done, but I didn't want it to be done. That's a very well-known problem. So in this case, there is no constraint that impedes a paper to be rejected and then rejected again and again and again and again. Sounds strange, like it's sadism, right? Anyway, so it's something we wouldn't like, and but it's a known problem. In fact, these two guys here, well, three actually, Goodfellow, Benjo, Courville, deep learning, yeah, they basically say that for decades, computer scientists were mad for programming, logic programming, which means like giving all the rules to the system that then would find the solution on its own. Planning, for instance, is a typical example. But when you do planning, you very often have to be careful to describe the word as accurately as possible to avoid that the solutions are actually sense-making, except they are rarely useful. Yeah. So people struggle to devise formal rules with enough complexity to accurately describe the word, or accurately describe the word. So, what did these guys then have in mind? Well, if we can't have enough time to describe what's going on, well, let the machines learn, right? That's why not only we have declare as a language, or declarative languages, say, okay, DPIL and DCR graphs and more, to specify the process, but it also uses description language of about what the process is going on about, right? Here comes declarative process mining. So, please welcome an event log, right? So this is a tabular format thereof. It's not XES. So we have a case number, case 1, case 2, case 3, and we have an activity or task, if you like, submit abstract, write new paper, submit paper, send confirmation email, review paper, etc. A timestamp and an actor, if you like. So the event log then is a discrete time collection, discrete time ordered collection of events. Discrete time, so time 1, time 2, time 3. One might say, hey, there is a timestamp, that's real time. Nope, hold on. It's not continuous time. We say this happens first, this happens afterwards. There's one after the other. It's an interleaving semantics. So that's why it's discrete time. Time in this case is just one attribute. Okay? So it's in a total order, and we slice it into cases. So there's like, there's case 1, and there's case 2, and there's case 3, yeah? So that we can have multiple traces to learn from. Because of course, if we only have one specimen, one run of our process, well, little can we learn, right? So, okay, well, what is the process? This one. What is one? Well, what you just wrote, yeah? It's like summarize, summarize the paper you've read for your assignment, and then you see the paper the same. Well, it's true. It's a perfect summary. It's just the same, and machines will do the same in this case. How many traces do we have? 1. So what is the process? That trace. So we need multiple runs of the same process to learn what are the common patterns out there. What's interesting is that, as very usually happens, especially now, computer science is branching out several fields, one after the other, and they tend to have their own life. But even from fields, also subfields emerge, and from subfields, subfields, right? Artificial intelligence, machine learning, deep learning, right? They kind of have their own life at some stage. And when they do, they create communities. And when there are communities, the communities have their own specific way to name the same thing differently. So what the process people call declarative process mining, software engineers call specification mining. And logicians in AI, like formal methods, they call it linear temporal formulae learning. It's always the same, just with using different terms, which is great because we can publish in different venues, selling the same product multiple times. Isn't that great? Yeah, so times 4, 3, whatever. Unless someone realizes that there is a strange comparison. But anyway, yeah? And what's also more interesting is that if you, unfortunately, I don't have a plot showing it, but the community tends to cite papers from their own, except process people, because they're cooler. So these other communities tend to kind of cite the works in their community, talking about the same things that maybe other communities did in the past. So we're going slow there, because we don't see still the synergies. And yeah, so it's a quite interesting feature there. So please, all people, do publish and use a universal language, so that basically everyone can understand. People in AI may stop considering, well, actually, process domain is just an application. No, it's not just an application, for sake. It's foundational research as well, but just put it well, and the other way around, okay? Cool, so that's why this gives a bit of universality to the concepts expressed now. And what time is it? Okay. So how to run discovery of the discovery process. Sorry, this is a bad terminology. How to run discovery tasks on top of event logs when we talk about declarativeness. Well, typically this is the approach, the Sherlock Holmes approach, the detective. We want to make sure to exclude things that are impossible. What remains might be reality. Yeah, so kind of. That's the approach. So we have an event log, this guy here represented as an event log, and we want to define the behavior of the process behind the event log. Define. I love this term because actually this comes from definire. It's Latin. And it means give boundaries. Remember this kind of. We want to kind of restrict the range around the possible behavior that a process can have. The more the constraints we discover, the more we restrict the process behavior that may be underneath the event log. Now, that's why the Sherlock Holmes approach. Every time we add a new constraint, we're discarding possible behavior. So this is not, no, that's not the case. So we add this new constraint that makes it impossible. Today, we'll see in the afternoon, we'll see 2 tools. The first one is command line. Yes, command line. Like in the good old days with green phosphor screens. Sexy. All right, so this is the first version we'll see, but it's good because basically, without having any GUI, we can use it for batch programming or for massive tests, because it tends to be faster, of course. And then the GUI version thereof, which is called room. So in case we want to have depends on what we want to do with it. We want to be very, close to the bare metal with our screwdriver, and use the terminal. Otherwise, well, there is the GUI. So the ingredients to do process mining with this specific approach, the declarative one. We need an event log, the rule templates, the repertoire. declare, for instance. If you want to go for DCR graph, please go ahead, but this is the same methodology, really the same. And the so-called process alphabet. We're now talking just about activities because we want to restrict our realm. It's also easy to handle. Like only talking about what you do, not the time, not the resource, not the, oh no, addition, the location, only what you do, actions. Easy. Then, please.
The domain of applications could be different than starting from a law, could be an auditing or every case of events.
Yes, of course. There is a researcher, her name is Mieke Jans. She's in Belgium and she comes from the auditing realm. Then she discovered process mining. She thought, well, I think we could make use of it for good reasons. Yes, indeed. So in the auditing realm, what tends to be more interesting is that there is a sort of, maybe that's not the case, but it's a sort of pseudo-adversarial regime. So if your organization wants to improve their processes for what we saw in the last few days, then they're keen on giving, well, not always, but they're keen on giving you the data for you to discover and improve their processes. When it comes to auditing, yeah, they're happy to give, it looks more like a sort of facial paresis, like, I'm so happy to give you my data, right? So it's, in that case, even more an investigation. But yes, definitely, that would be absolutely stunning. Say, for instance, if you want to check that some rules, some laws are never violated, there we go. We express the law as in terms of, if we can, declarative expression. We check how much it is supported in the log, and if it's not enough, then raise the red flag. But that's indeed another great example. Thank you. Thank you so much. No pressure, but are there billions questions like this? If not, shut up. No, just joking. I'm joking. Any questions? All right. Cool. So how to proceed? Well, let's begin with a brute force approach. The brute force approach is, let's take every constraint template. We saw that most templates, aside from some interesting dialects, they have either one or two parameters, yeah? So what do? We take every possible action, we stick it into the variables, the parameters there, and we check with a combo, like, I don't know, respondent existence. No. Respondent existence is a template, yeah? And with this template, we can have it one AB, AC, AD, AF, BA, BC, BD, BF, etc. So we basically try with all the possible combos, and then we start measuring in how far they hold true in the log. Remember, 95% of cases, if you submit your paper, you get a review. 95%. So now there is another strange, well, not strange, but interesting twist to this. When we assign, especially in empirical sciences, the measure itself is not given a priori. We have to find a measure that is qualitatively good enough to express in how far your rule is true in the log. There is not one measure, of course. We counted out, at least in the association rule mining realm, there are about 62 different measures, which you can use depending on what is your sense of being fit for purpose. Yeah. The most known ones are support and confidence. Support does the following. You take all the events or all the traces, you put them at the denominator. At the numerator, you put how many times your rule was satisfied. Confidence instead, and here comes the brilliant question of Håkan before. Confidence is the same, but at the denominator, so down, you don't put all the events or all the traces, but only the events or the traces in which you had the activation, so the if part. Okay? Cool. So then we set a threshold. We say if, or more thresholds. If our measurements are such that the, a constraint falls behind the threshold, then we cross it out. Sherlock Holmes, right? So what is basically not sufficiently credible, then can't be the case. Out. Then, remember what we said some time ago. So we had respondent existence AC and response, which means if A, then C, but I don't know when. This one says if A, then C, and I know when afterwards. Between the two, what is the one that gives you more information? I know it's a hard question to ask, but there is coffee. So the stricter one, which is among the two? The one that says I don't know when, or the one that says I know when after? Right? So keeping both tends to be quite redundant, right? And you'll see today in the afternoon especially, if you keep all the redundant information, there are some compulsory collective people like me that tends to collect. I mean, have you seen that? I have 2 mobile phones just because I'm I don't want to leave one out. It's still working. Why should I throw it away? That's kind of me, right? That's redundancy at its worst or its best. Besides, also hit the microphone. I'm sorry. Right. So, but in this case, if we let the machine learn all the constraints and we don't get rid of the redundant ones, we are overwhelmed by information. And then finding out what is really interesting is very hard. Okay? So that's why we care about minimizing the number of constraints we have. Yeah? This is something completely new that does not, rarely exists for the imperative counterpart. In that case, we want to simplify paths, right? Which doesn't mean that we simplify the behavior. In this case, we do. Sorry, hold on. If we simplify paths in a BPMN model, we lose something. There was a transition, I crop it away, it means this cannot be done any longer. In this case, instead, we're keeping the same information by cropping constraints. Huh? It's like re-expressing the full thing with fewer words. Okay, cool. Right, so then I'll remove then, I keep response AC and I get away response existence AC. That's it. Whew. Cool, right? Yeah, so how do you compute these measures? Now, it's interesting. Believe me, until 2021, depending on the paper you read in Declarative Process Mining, you would have different computation modes for the same measures. And if you're asking yourself, but are the results the same? No, of course not. That's interesting, right? So every bunch of researchers had their own idea on what the measure was about, and they did their computations. Still nowadays, today in the afternoon, we'll use 2 systems. One is the terminal one for hackers, and the other one is for computer scientists more elevated. Yeah. Final users. Thank you. For final users, we use the GUI, but the way to compute support and confidence are not the same, which is, sick, but it's the way it is. So, then in 2021, we came up with the community came up with a theory. So, this should be the way to compute them. Full stop. To compute them, we could say, just count how many times the constraint is satisfied, and that's it. Right? You just said that. I just said that, right? Is it? No. Why? Well, let's look again at this guy. B implies next C. At this stage, and at this stage, and at this stage, they were true. This was true just because we didn't read B, right? Since the actuation is not there, then it's true. And now, let's see an example, yeah? All right. If you see a unicorn, right? So it's blurry out there. Maybe you drank too much beer or other things the day before, and you see a unicorn. And I say, if you see a unicorn, then it's green, not pink. Sorry, I changed the color. So then what I state is true. It's universally true. And why is it? Prove me wrong. As soon as you see a unicorn in front of you and you bring it to me, then tell me if it's not green. Now, what's interesting is that recently I've had a strong opposition at home. And, okay. So, why is it of interest to us at all? Because this is really a curse. If we start injecting in our output constraints that are there just because they were never violated, it could be that we, again, clogging the results with things that mean nothing, or mean something but of really little interest. For example, imagine we have our friend coming over again, the unicorn, yeah? So, if you see a unicorn, your paper will get accepted. Stop, no, don't run around. Stay here, please. Now, this is true because you can't prove me wrong. I mean, unless you see a unicorn and you don't get your paper accepted, then blame the unicorn, not me. But anyway, that's the idea. So I'm exaggerating, but you got the point, right? So giving rules that really are never activated as if they were true. Well, yeah, technically they are true, but of what interest are they? Yeah? Okay. So to kind of solve the two things, so how to measure universally support and confidence of constraints no matter what, and try to exclude this kind of, they're called vacuous, you know, like a vacuum cleaner. Yeah, the vacuous constraints. They basically absorb your time, giving you nothing in exchange. We have come up with this idea. What if we take for every template and every possible LTLF formula, we can do so, a normal form that it's a sort of implicational normal form, pseudo right now. We call it reactive constraint. So we express everything in the form of always true, that if then. If we're able to do that, and we can do that, then we can resort to an incredibly large literature in association rule mining, giving us exact formulae to determine support, confidence, lift, coverage, and whatnot. Yeah? Because they are, in the end, like if you buy a book from J.K. Rowling, then you are also interested in Lord of the Rings. Yeah? So let's look at it. So this is the response AC guy. What we do is also to change, to give a bit of an allure of noble arts. We also change the symbol, so we put the always here, so as to simplify things a bit, but it's the same. And we call this reactive constraint. So activation is A, next eventually C is the target. They're both LTL formulae. This one is a bit more, oh God. This one is a bit more trivial. It's just a, a term made of just a single propositional symbol. This is instead a proper formula, but in the end they're both formulae, right? And then we say, well, look, in this case we can discriminate between three states. So we are used to Boolean logic, in which is like it's true or false. Now here it's still true or false, but when it comes to determining measures, we consider three possible states. The first being, interestingly, just satisfied. What does it mean? Well, you meet an A, so this instant has an A, and you also have a C afterwards. As opposed to the unaffected, where you say, well, the constraint is true just because there is no A here. Okay? And, well, there is also violated, which means this event is A, but there is no C in the future. Yeah? So if you receive a payment, you send an invoice, right? No payment, no payment, no payment, no payment, unaffected, unaffected, payment. Is there an invoice later on? Oops, I forgot. Yeah? Oh, tax fraudster. Anyway, happens. So that's a violation. If instead we have here a payment and a few instances afterwards we meet, oh, nice, this is the invoice, then satisfied, interestingly. Okay? So what happens then? We can basically do it through the entire trace. Now, and here comes what we said before. There are two kind of different schools. There is the school of the strictest. They say, in the whole case, it must never be violated. If it's violated at least once, then the full trace is violating my rule. Okay? So the process run. One violation, the full run is violating. There are others instead who say, well, look, take into account that maybe, but this is cool because it can rapidly single out exceptions, right? Others instead say, well, it could be that there is a glitch in your system, so you record events like flipped, maybe, swapped, not because they were like that, but because the recording was like concurrent and it just went the other way around, or there are some things that are not written. So let's try to take an approach that basically gives you a degree of satisfaction inside the trace. So trace-based, this trace is violating the constraint. Why? Well, because we have an A with no C later on, right? At least one. So it's violating all in all. But in general, we can basically dissect it and see, well, this guy here actually is like unaffecting the constraint. This is affecting and satisfying, unaffected, 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 satisfying, unaffected, violated, unaffected, right? Cool. So if we have this, then we can come up with support and confidence, just like that, right? Because we have support means you have to average over the number of events in a trace. 2 out of 9. And I still don't know why I used 9. It could be 10. Would be so easier, but no, 9. Fair enough. Okay, so 2 out of 9, so 22.22%. Confidence of response is instead like averaging over the number of activations. 1, 2, and 3. Out of 3, 2 satisfy. So 2/3, etc. Okay? You just have to withstand 7 minutes to your coffee. I know it's tough. Just to make things easier, right? Okay, this is basically on steroids. As said, we have 2 different ways to compute these measures, trace-based or event-based. Anyway, when we talk about logs, things repeat, right? So it could be a given trace occurs like 60 times, another one occurs 6 times, another 10, another 24. Yeah? So we basically multiply the occurrences of a trace to dictate how many times the violation or the satisfaction or just the occurrence happened. Yeah? So here we have 1 satisfaction out of 1, 2, 3, 4, 5 events of a trace that occurs 60 times. Right? So it's 60 out of 5 times 60, so a fifth. If we go just trace-based, since this is the only trace satisfying my response AC, the others don't, then 60 traces satisfy the constraint over 60 plus 6 plus 10 plus 24. Right? I mean, it's not, high mathematics. It's just we're counting. So far, so good? Okay, cool. Then if it make it event-based, then we have to be a bit more fine granular. So, we have to be finer granular because it's 1 event, this guy, over 60 plus 1, 2, 3 times 24 over the sum of all. Yeah? Confidence, same story. We have 60 plus 6 plus 24 traces activating the constraint. This doesn't. So it's 60 over 90. Event-based, it is the same story, just with events. So it's 1, 2, 3, 4. So 1 times 60 plus 1 minus 1 times 6, because it's like this A. 4 minus 1 times 24, because it's like 4 events, out of which 1 is violating, over 1 times 60, 1 times 6, etc. That's it. Now, I know, it's boring. We're yawning, perhaps. We're thinking of, I would like so much my coffee, or why didn't I sleep more? Yeah, but this is kind of straightforward. What's good about it? A machine can compute it fast. Remember, we are into process mining. We give to machines the task. If they take forever to compute the results, then it's very unsustainable, environmentally unfriendly, at least, right? Not to say boring. So we can extend the approach to all existing constraints and beyond. So if you invent a new declarative language, which is just top notch, we can still apply this because we can reverse the formula in an if-then form. Yeah. So take-home lesson: we can now. Yes, we can count and make divisions. Great. Aren't you happy? That's what your gradation is about. So then what? I hope to come here after the coffee, but instead. Anyway, so I'll just fly through it. 1 constraint we know how to measure. How about full specifications? So multiple constraints. Look at this just to get a bit scared, but the concept is simple. What we do is we take all the activations. So for every constraint, we take the activation. And we say, if at least 1 constraint is activated, then the full specification is activated. For instance, if you receive a payment, you must send an invoice, as a rule. If you if you receive a loan request, another person should check it, not you who received it. Yeah? So they have to be both engaged, maybe not together. So if you receive an invoice, receive a payment, the full specification, like, there is something to check here, even though it's just one of the two rules. Yeah? So to trigger at least one activation. To satisfy, this is outrageous. Let me tell you. You pick the rule that was activated and check that it's satisfied. Not all the rules, just the one that was activated, right? So this not and not blah, it's just to represent an or. That's it. So at least one activation triggered, none of the rules falsified. Okay? So far, so good? So then, since we have this setting in which we can say if it's satisfied, violated, or just unaffected, none of the rules is triggered, then we can apply the same framework again. But not to one rule, to full specifications. Yeah? You see the point? So, interesting fact. So, remember the threshold? If I say I want only constraints that have a confidence of 95% or more, would be here. Then I expect, or let's say 90, it's more fun. 90 is also acceptable, right? So I expect that all the constraints have a confidence of at least 90%, every individual one. But is my full specification made of all constraints made of a is the confidence of my full specification of all the constraints that have a confidence of at least 90% also 90% or more? I repeat the question. You have 4 rules. This code from the event log. All of them have a confidence which is higher than 90%. What is the minimum confidence for your full specification? We have a room here in which everyone is at least 10-year-old. What is the minimum age in this room? That's not the case. Here, since the framework was not well determined, it happened the following. We take all people of 10 years or more, but the final community tends to have tend to be 9-year-old. What? Yes, it's strange, right? But that's what happens. Look at this bar. Yeah? So you see that basically the threshold is growing. It's a dashed line. And the bar, which represents the overall confidence, is below that, which means that although your threshold was 0.9, in the end, the final confidence was less than this. Damn it! Right? So this is interesting, I think, to express. So watch out, individual rules that do not necessarily imply that the full specification is does at least have that confidence. Another nice trick, I'm just now showing, fetching some images because the hardest part is over. So, here we talk variance. Yeah, we talked about variance at some stage for the variability. Well, variability is because of variance, right? So, how to determine what's different, what's varying between the two models here? Well, we have a red line, so I guess it's pseudo easy for us to catch, right? What's the difference? Guess what's going to happen now? Could you please find me exact pinpoint what the differences are in terms of behavior? Well,
What in the back?
yeah, right. That's the difference. Tough, right? So, what did we do? We basically run our measuring on both sides to determine what are the typical constraints, and then we checked the highest differences in support and confidence, and then took these rules and compared them, right? Then, to avoid any bias for the statisticians among you, or probability theory people, we not only did that, we also tried to, mix up slices of the traces to check if actually this difference was random, to avoid that part. So in the end, we just show this, like invariant A, it is 37.4 more likely with confidence than invariant B that admission and C occurs in the present instance, and all that. So we basically show the most, relevant differences between them. Again, just because we can sum and do divisions, but if you do it right, well, works good. Now the one is after the coffee break, I'd say, because we have drift reduction, but this really requires a lot of attention. So if you wish to stay with me again for a long time talking about this stuff, I would rather push our energy and sustain our morale with exciting liquids. Yeah, cool. Welcome back from the coffee break. Can I start? Great. So we begin with a brilliant observation of one of the people in the audience. Thank you, Marcos, for showing. Actually, yeah, indeed, I can count and do divisions well to some extent. So actually, 60 out of 100 is not exactly 70%, but roughly. Anyway, yeah. So to begin with, right, just to restart from where we left. So the idea is that now we are using a new approach to describe, to define the behavior of a process. This is called the declarative approach. We use basically constraints to restrict the behavior. Constraints that are more restrictive are more informative. One thing is saying if A happens now, the very next instant will bring B. Another story is saying like if A now, then eventually B. The former is stricter. So if both of them are there, we tend to prefer the former than the latter. Okay, to the latter. Then we have found out that we can express any LTR formula. So even if you want to customize the declarative language with your own specific formulae, you can do that. And still we have a way to compute support and confidence and whatnot out of there. How? By creating rules that are expressed in the form of if A, or it's always true that if X, then formula. If we do so, we're done. Okay? So this is indeed a weak way to express that. But yeah, I know it's a bit tough to show it. But even if you have like, oh no, we impose that the first event must be A, where is the if? The first event of any trace must be A. Where's the if? The first event of a trace is A. Express it in an if-then way. Is there a manner? Well, it's not so intuitive. That's why some slides ago we said start. Start means now. So we can tell if start, then A. See the trick? So basically we're using this kind of if-then form in order to make it always possible to express the rules in that way. All right, so then we went through this particular complication to make it such that we can compute also a sort of big if and big then for full specifications. Reminder, a specification is the set of all rules that must hold together. True. Yeah? So if I say, like, I am a human being alone, that can be defined as true, I think. But if I say I'm a human being, and by the way, I am Napoleon Bonaparte, well, not really, right? So one of the two statements is true, but the second isn't. So, well, that's the problem, right? Or every time you receive a request for a loan, then the checker must be another one than the one who received the request. And once you give the amount to the requester, there should be a subtraction of taxes. If we fail with one of the two, well, actually we're not compliant with the law overall. Even though one is actually satisfied, the other is not. So this is the idea, okay? So we want to give a quantity, a number, to express in how far, not one constraint, but the full specification, actually adheres to the event log. We're talking about process mining here, so we assume that we have at least as a sort of source of information an event log. What was the trick here? I'm trying to do a recap to recover after the break. Yeah? So let's see. So the trick is we take every activation, the trigger of every rule. If one of those, at least one of those, yeah, is satisfied at a given instant, then the full specification is activated, right? So or A or B or. Then we must make sure that none of the constraints are violated. At least one is activated, and then none must be violated. That's it. If that's the case, satisfaction. If there is at least one violation, violation. All right. And we saw it was quite interestingly happening. So we didn't care about this a lot in the past, and therefore we have existing minors. Besides, Terracotta, this guy, is actually not, which means like baked dog. Anyway, so Terracotta is a tool in software engineering for specification mining. So, and they also suffer from a similar issue, right? So here we see the threshold. The full specification is not going above the threshold, but below it. Although all the constraints it's made of have a confidence that is at least higher than that. Quite interesting. The other two names you might be able to read here are named Janus and Manifold, and these are instead like process specification languages for the process mining realm. So we went then to the usage of these measures also to discriminate between variants and dictate what is the difference. Again, if we have numbers, they can be used to find the highest deltas between constraints to the left and right side. And then the harder part, drift detection, right? So variability also implies that over time the process evolves, right? So processes are not, going to be forever the same. First, because we are humans, so we tend to change things in the long run. Second, because we want to improve. Improving means changing, typically. It's hard to improve staying static. And also there could be new exogenous factors, new laws coming in that impede the process to continue as it did before. The famous Sarbanes-Oxley Act is one of these examples, right? So we have to change things because the law says so. So we have drifts, the so-called drifts, so which means like the process changes over time. Now, how to detect them? Not easy, right? And especially detecting what changed is also another nice issue. So what did we do? We computed, well, here it was confidence, but we could use any measure available. Confidence for all the constraints. So on the what's that? To the left-hand side, they're just IDs, numeric IDs for all constraints that we mine. The purple one, the violet ones have a very low confidence, close to 0. And the yellowish ones have a very high confidence, close to 1 or 1. Yeah? So how to determine there was a drift? Well, guess what? If we imagine you have the event log, yeah, and you slice it over time. If any of us has been into event stream analysis, we might remember that it's like the window moving, right? So we have a buffer analyzing over time the stream of events. Yeah, can be also tumbling window, anything, any form you wish. So we slice the event log into traces over time. Traces are complete, but we slice them. We slice the event log in sets of traces. So if in this batch the confidence of response was 100%, and in the next batch it drops down to 70, perhaps that's a drift. So that rule that held before, now it doesn't hold anymore. That is why we have these vertical lines here. Vertical lines basically determine that there are some drops or sudden rises in the confidence level. Now, this is cool, right? Because, well, I think so at least. Because it means not only we determine there has been a change, but we can also say why there's been a change, right? If we have a full process model, it's not so intuitive. It really looks like a sort of so initially they call it settimana enigmistica. It's like one of these papers that you use basically on the beach, seaside. You find the differences between two pictures. That's one of these, the rabas and so forth. So that becomes a sort of game. In this case, no. Actually, it's the system telling you there has been a drift and the constraints changing are these ones. How do we do that? Well, we take the most erratic differences and say, hold on, there has been a change here and there and there and there in this constraint individually, right?
How do you know it's not a false positive then?
That's a good point. I have no clue how to discriminate. This is a very interesting question. What do I mean? The first off, we have an issue with the sense of error, meaning it could be that there is an error in the recording of the facts because there was a wrong data entry. So this is basically a fault in the log. But if instead it was because actually the operator forgot, that's a fault in the execution, so in the process itself. Also, it could be that maybe the entry was correct and the behavior was correct, but the system swapped events. So we could say, well, if an event is rare enough, then it doesn't really matter, does it? Well, imagine the event is like the thermoregulator of your nuclear plant is going beyond a certain limit. Well, that's rare, but I wouldn't take it like, it's just noise, right? We'll come back to that. So it's an excellent question. I don't have an answer though. And I presume that the answer here would be, however, less related to techniques and more to the so-called human in the loop. So someone who has the necessary knowledge to let you discriminate between errors, false positive, false negatives, because this is more a validation step than a verification step. But that's an excellent remark.
It happens to me really frequently because I work in fraud, and I ask that because of setting those thresholds.
Yeah.
They require manual intervention of an expert analyzing that, but I want to see if there was something.
I'm so sorry. No, even there's also been a offline other question about how to set the thresholds, how to tune them. We have an idea, but it's not yet, how to say, implemented, because it involves techniques that we are not really aware of yet. Basically, to strike a balance between the maximum increase of informativeness, so interestingness in things that happens after the threshold. So it should be like a high peak. But it shouldn't be a high peak from 0 to 0.1. It should be like in a higher position. So it's interesting. So maybe one day, once we have this mechanism, we could also teach machines to auto-tune. But yeah, it's still at its infancy. But your contribution is very welcome, of course. Right. So well, to come back to the drift detection then. But thanks a lot, really. Not only we can pinpoint essentially the constraint having issues or hurdles, but we see also something interesting. That is to say that the constraints that are more erratic tend to have also set effects on the full specification. Yeah. The reason being, since it's just enough that one constraint is violated that basically the full specification is alerted with a violation, then we can see that there is a sort of reflection mechanism also over the full specification confidence. And this is also more interesting, to me at least. So confidence and support are widespread and well known, but basically association rule mining has been studied for decades. Possible measures and their application, in which cases and so forth. Now that we have this powerful engine to compute the basic probabilistic sides of every constraint, given the if and then format, we can apply all of them. So our question was then, well, what is the best performing measure when it comes to detect drifts? Well, it turns out, again, we saw that the precision, right, was kind of, floating this way in presence of drifts. But if you look instead at this one, I was not aware of it at all. I just discovered this thanks to the experiments. Sebag-Schunauer, this one, look, it tends to have the same trend, just it's amplified. See? Peaks are more amplified, which is great because basically it tends to be instead kind of flattened out when the others are flattened out. So this is nice, which means if we want to detect drifts in our system, in our process, maybe let's use the Sebag-Schunauer rather than confidence, which is still valid, but maybe not the best. Bing! Star. So this was about measuring, being effective, being performing, and all that. Wow, fantastic. But then, now we are presented with our results. We can detect drifts, so how can we describe the result to the end user, for instance? And here comes an interesting issue. We said there was an is-a hierarchy, and constraints are not orthogonal. I know, it was 9 a.m. today in the morning. We're probably still kind of half sleepy with the pillow still here on the cheek. But the idea was like the constraints tend to be more restricted than others, can also have some side effects. So in the end, just like laws, we could have contradictions. Right? So let's see. Let's imagine what happens here. We have a specification. It's also the curse of LTL versus LTLF. Okay, this is a famous manager of a nuclear plant and gets instructed about this. So if you see a temperature alert, set the engines to safe mode. Okay. Once you set the engines to safe mode, call the emergency squad. Okay. As you call the emergency squad, log the system error. Thank you. Every time a system error is logged, immediately set the engines to safe mode. Easy, right? So basically, we got all these 4 rules together. So far, so good? Now, there is a temperature alert. Set the engines to safe mode. Then call the emergency squad, because it was like, if you set the engines, then call the emergency squad. But if you call the emergency squad, you log the system error. And if you log the system error, then you set the engines to the safe mode. But if you set the engines to the safe mode, then you call the emergency squad. And if you call the emergency squad, then you have to log the system error. And if you log the system error, there's a system error. Ow! Then you have to set it. Now, unfortunately, the PowerPoint doesn't show you, but it was like Homer running back and forth every time. But yeah, fair enough. So, you see the point? So these 4 rules were not contradicting each other. I mean, not explicitly. But you can't satisfy them all in a finite time. Right? You need an infinite run. So this is one of the situations that we might fall in if we don't pay extreme attention to the facts we extract from data. We could even contradict or come into situations that are simply unsatisfiable, we say, right? So basically, the issue is here. So we entered the temperature alert to the safe mode, emergency squad, system error, safe mode, etc. So there is no accepting state. I mean, this is when Homer is happy and is basically doing the run, what's that? The wheel on the floor. Okay. If we thought, well, okay, fair enough, but this is clearly a made-up example. Does it really happen in reality? Nah. Well, this is really what happened to me when I was ending my PhD. So it's about 10 years ago. And I was sniffing event logs out of email exchanges. 10 years ago, it seemed like half legitimate. Nowadays, it would be barked by squads of dogs like GDPR, GDPR, oh! Right? So all the time. But now, well, back then it was still fine. Well, I think at least. I didn't got sued anyway. So I was kind of, processing this log with the machinery. I put some thresholds again, as always, like 0.85 for support, 0.25 for confidence, 0.25 for interest factor, and so forth. And I came up with this list of constraints, pretty unreadable. I mean, even if I zoom in, it's still pretty unreadable because can you imagine like reading all of them and remembering them? It doesn't really work. So even the transposition to the full-blown automaton is not really more readable than that. So, apologies. Basically, I wanted to avoid this. That's not the same one-to-one. I wanted to avoid this one, and instead I came up with this. Not a big step ahead. So still I wanted to see instead if, basically, based on the conjecture before, right? The fewer the constraints, the more messy the automaton. So perhaps the more constraints, the least messy the imperative version, right? That was my hope. So what did I do? Well, I started looking at all the constraints that pertain to submit draft. and created an automaton out of it. Then all the constraints that pertain to write deliverable, and all the constraints about organizing agendas. So basically I have little pieces to mount together with a final result. Knowing that it would have taken a long time, but I was still curious, right? So it was loading, going on. I could hear at some stage the fan of the laptop. In the end, bing, you know, like when the oven is done. Right. So, in case this means nothing, literally, so not nothing, it doesn't have a meaning. It has a meaning. You can do nothing, right? So, the start state is the end state, and by the way, it's not accepting, so you can do literally nothing, right? Oh, come on. Why? This is the curse of inconsistency. If there are inconsistencies, meaning there are rules contradicting or pockets of rules that altogether contradict one another, like the the nuclear plant issue before, right? In any case, this results to the fact that there is no possible execution that can satisfy all the rules together. And if we say there is no possible execution that satisfies, if we say that there is no possible execution satisfying all the rules together, you can do nothing. There we go. Can you imagine now? I had to find the needle in the haystack, literally. So what is the constraint running this all? Good luck with that, right? So I got curious. I thought, how can I just reproduce this issue? Because after all, there was an event log. So there is a way to execute the process. The event log is there for that, right? I repeat. If there wasn't any way to execute the process, how can the event log exist? That's an evidence that actually it was run. So there is a mismatch. So I did the following. I created just a few traces like that, A, B, A, etc. I set the confidence, I wrote support, it's wrong. Confidence is like set to 0.7. And then I start. So A is always the first, 100%. C is always the last, 100% as well. In 6 cases out of 8, so 75% of times, C does not directly follow A. You can check it on your own, right? So we have 1, 2, 3, 4, 5. Hold on. 1, 2, 3, 4, 5, 6. Something doesn't work. Oh yeah, all right. So 1, 2, 3, 4, 5, 6, 7. So also counting the C's, yeah. So it happens that basically A is not followed by C in 2 cases out of directly follow. Okay, 1, 2, 3, 4, 5. Yes, good point. Now I see. Okay. This one satisfies because it's AC. And maybe somewhere else. Let me check. What did I do wrong here? There is something silly. 6 cases out of 8. Ah, right. Sorry. That's it. That's a trick. No, watch out. Sorry. If we count these 8 events, A and C's, yeah? So, violation, 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 4, 5, 6, but these 2 satisfy the rule. That's why it's 6 out of 8. Okay, now, in 5 cases over 7, so it's like 71%, still above the threshold, C is not directly preceded by B, so we count B and C's. So 1, 2, 3, 4, 5, 6, 7, and C is directly preceded by B only here. So in 5 cases out of 7, we do respect the rule. So it's 71%. Now we get rid of those, and we see that the composition of these 4 actually is the empty one. Why? This is tough, so bear with me. Good that we had coffee before. We have 3 activities. A, B, and C, all right? Or A, B, and C. Now, the first one is A. The first one is A. The second one is C. But between them, we can't have C nor A, and we can't have B either, right? I can't get B before C, but I also cannot get A before C. So what can precede C? Nothing. Meh. Hence the issue, I repeat. The first thing you do is you enter the room. The last thing you do is you exit the room. You cannot see it. Right? So in this case, if you have only 3 actions available and stand looking like a dump is not an option, then it's inconsistent because you can't do anything at all. Right? Does it convince you this is not easy? So we can't really manually inspect all that, because if it comes like out of 4 constraints, it might be easy to check. But if it comes out of, you know, this bag of whatever, then it becomes a bit more tricky. So there we go. Out of there, which constraints are in conflict? From where should we start? Can we avoid to check the same sets again? Because if you go, you know, brute force, we try all the subsets of constraints to see if we pick some inconsistency, then we say, ah, yes, found out. Great. This is the explosion to XP time. So we don't have all the life to wait, so at some stage we should say, well, we have to find something more, something quicker. And how can we make sure that we find them all? Right? One thing is being fast and finding at least one conflict. Another, which is soundness. Another story is about completeness. So can we find them all? So, and there is another problem, redundancy, right? So, let me check. All right. A is always the first. All right. C is always the last. Okay. Before C, A precedes. Hold on. Before B, A precedes. After A, eventually C follows. And after B, eventually C follows. Okay, right. So, what is the trick there? If you start with A, every other action needs A before. Right? If you end with C, every other action will see C after. So why repeating this again? It doesn't make sense, does it? Again, look. If A is always the first, why do you say, well, before C I see A and before B I see A? Of course, it's the first. Come on. It's there for a reason, right? Same story here. Now again, you might think, oh, okay, but this is trivial. Yeah, I can live by. I mean, it's just a couple of constraints more. What's wrong? Remember, right? So can we also make it that such that in one go, I get rid of the conflicts and the redundancy? Notice, this is a different problem than before, right? So far we wanted to make super cool, fast, performant, interesting in our results. Now, it's also about how to reason, automated reasoning, on top of these results to make them a little less hard to digest for human beings, yeah? Cool. Again, from where we start, how can we make it efficient, etc., etc., etc. So, here we have 2 ways to tell the solution. I know you're vibrating by excitement at this. So 2 ways. The first is like talking about automata product monoids, which is an algebraic structure with composition operator, holding the properties of commutativity, associativity, and bearing identity element and absorbing element. Or go in video games. All right, so let's put it this way. So the solution is quickly the following. Imagine you have a set of constraints. They express their own language, we said, right? So all the executions you can have. If you add a constraint, you can do fewer things, right? Exactly, it should be like that. So we expect that by adding a new constraint in the question, then the language shrinks. What if it doesn't? So you add a new constraint in the pot, and the language stays the same. Like, What? Did it? Exactly. It's redundant. That's a trick, right? You just try adding one by one, and if you see the language just stays the same, well then there was no reason. Add a new constraint, and then it shrinks. A new constraint, language is empty. What happened? Contradiction, conflict. Just this. So in the previous slide, the boring one, we mentioned one operator, composition operator, this X. X is the synchronous product. The synchronous product between automata is the AND, the logical conjunction between formulae, okay? It's the same. So this one is commutative, meaning that if you take one constraint and then the other, or you swap them, the result is the same, commutativity. This is cool, because it means you don't have to start from a precise point to get your results. You can start from wherever you like. The other one is associativity, which is even cooler. Why is that? Associativity means if you take two constraints and you add a third, or you take the first one and you add the other two, it's the same result. Shall I repeat that part? Think of the addition, right? 3 plus 5 plus 2. Result is? 10 is either 3 plus 5, 8 plus 2, or 3 plus 5 plus 3, 5 plus 2, right? So you can basically merge the result with intermediate outcomes as you wish. Associativity. For us, it's great, because it means you don't have a strategy, predefined strategy to grow your analysis with other constraints. It doesn't matter. With commutativity, it means you can basically start and end wherever you like. Woohoo! Now, sir.
So are you implying that it doesn't matter what rules you remove, the meaning of the final set of rules will be the same?
That's an excellent remark. What I'm saying is the rules you add, you can add them in the order you prefer, the results will be the same. If you remove things, it's a different composition operator, right? So, no, I'm not saying that, because actually it makes a huge difference which one you pick out. So that's a great remark, but no, that's not what I'm saying. But thank you, right? So, but because it's a very picky question, I repeat. Here, what we're stating is that the more you add, the results doesn't change. But removing is another story, right? Let me.
I mean, if you start from different rules, adding new rules, when you finish the composition,
yes,
the set of rules that you have the same meaning if you start adding the rules in a completely different order.
Exactly. The final result is the same.
Yeah. Even though they are not the same rules.
The set of rules altogether are the same, yes.
What I mean is, maybe you don't have at the end you don't have the same rules, but
why not?
Because if you add rules,
yeah.
For example, in your example, the first two rules are equivalent to, I mean, the number 3 and 4 are equivalent to 5 and 6.
Yes, good point. So I can exclude either this one. So this first one, if we only have 3 activities, it is equivalent to this 2. Yes. Right? And this is the same as this one. So clearly, either you pick out only the first, or you pick the other 2. That's a great point. But what I'm saying is that I'm not yet picking anything out of here. I'm just adding them all together. The result will still stay the same. Either if I start from the latest and go to the first, or the other way around, or composing. That's a great remark. It will have indeed an effect on the discussion of the results. But thank you. That's great. It really is. Okay? Now, I'm really poking you now with very difficult things. Identity element. What is it? The identity element is like 1 for multiplication, 0 for addition. In our case, we're talking about constraints. If you had your pot of behavior, your bloof, a new constraint come in, and the pot stays the same. That's an identity element, i.e. a redundant constraint. So the identity element is the either the redundant constraints or basically this guy here, which says you can do anything you like. That's a spectacular constraint, and that's an identity element. If you cross-check, do whatever you like with constraints, well, the latter matters. The absorbing element, instead, is you can't do anything at all. This is nice because it means that as soon as we find out one conflict, it must be it. There is a clear evidence. So if we put a conflict in the pot, it won't just reduce the language. It would annihilate the result, okay? It's like having a multiplication of 1, 2, 3, 5, 4, 5, 4, 3, 5, 2, 0, 0, right? Cool. So, we went through this already. Let's start. Monoids. I don't know if there are retro gamers in this room. I am, so that's why. Cool. So, our energy bar here is the amount of information we bring. Again, the fewer things we can do, the more the information we have about the process. A process in which you say, well, your organization can do whatever they like. Thank you. That's very informative. I mean, I've been parsing your event log for hours, and this is the result. Right? So, restricting the behavior means we have more information. Ideally, we want to have this bar to increase at every new block that falls. The block that falls is the new constraint we add. Okay? When they touch the ground, yeah, we compose the two and we just store not the individual, we don't store the individual constraints. We store their product automaton, so they all birth together. Okay? So, software developers, I'm talking about you now. If you want to optimize your memory consumption, it means that you don't have to store all the automata together. You just store one automaton, which doesn't save much, we'll see, but anyway. Then there is a new constraint falling. We do the product automaton and we save it. The information is increasing. Yeah, see the bar. Now, the cool thing is that at this stage, the first one was taking advantage of associativity. It doesn't matter how we mix up constraints together. The result stays the same, so we don't have to store all of them. The association, the combination of them will be enough to be stored. The second one is commutativity. We can either go for passing the purple and the blue, or the blue and the purple. It's still the same story. Doesn't really make a difference. Then the product automaton keeps on growing and growing and growing and growing. If there is a conflict, how do you see that? Thanks to the absorbing element. Now, why does the information bar here drop to nothing? It's the opposite as before, right? So I've been testing and processing your data for hours. When I say hours, it's actually days. And now finally the machine can tell you that the organization can do nothing. Just, go bankrupt, close, shut down, I don't care. Thank you, right? So that's not what we want. So we want to basically do something that is typical of either we go game over or we remove this conflicting one. Watch out. Conflicts are therefore certainly removed, but there are multiple ways to remove conflicts. Okay, so it's not necessarily just because it's the last one we saw, this is the one we remove, which doesn't mean it's the only one to be removed, which is exactly what we were talking about before. Composition is one operation, removal or complementing is another operation. Subtraction, yeah? Redundancy. Why is redundancy so bad? Now, we're moving from the metaphor of Space Invaders to the one of Tetris. So, if the bar doesn't increase, but new constraints are popping up, we basically end up in the game over because we go to exhaustion of a full screen, which again is something we don't want. Again, why? I've taken days, when I say days, weeks to process your data, and actually this is the result. Where is it? In the other room. It's like 3 books of constraints. Ah, no, thank you. Thanks a lot. Right, it doesn't really make any, it's not efficient. It's impossible to take all together, right? So we have to remove redundancy, especially because many of the things written there are not even informing. They're just repeating the same concepts again and again. So again, we want to avoid redundancy. So with this trick, taking advantage of commutativity and associativity of the product, then we can remove inconsistency, minimize, not getting the minimum, right? Minimizing best effort redundancies, analyze each constraint once, which is cool. Rather than trying with the subsets increasing, it's quite a boost. All right. Good. So, well, then, some plots just to show how cool we are. Yeah. So, there was actually 2 challenges there. So the first was, well, does it really scale? And these plots just nicely grow. It looks like, wow, this is like my annual income. No, actually, it's something different. It's the amount of time it takes to find the possible inconsistencies and redundancies. But the issue is that the product operation is non-monotone. Monotonically increasing or decreasing functions basically translate to the following. If I add new constraints in the pot, the automaton grows. No, it's not the case. Indeed, it can shrink to nothing. Not only that, it could be that we add new constraints, the automaton shrinks, then gets larger, and then shrinks, and then gets larger, you can't control it anymore, up, Stack Overflow. So it's really non-controllable. That's why this technique is working. We'll see that today in the afternoon, but it's not being the best performing one. There must be other solutions. We'll see some in a few slides, but yeah, the challenge is open. And by the way, this is a reasoning task that goes beyond process science. This is basically AI in general, right? So it's quite a nice, battleground, if you can forgive me for this term. And I think
you have an intuition of when does it grow?
That's an excellent remark. So it tends to grow if we add constraints that specify operations that before were unconstrained. So if you say you can do whatever you like, it's as if every state has a sort of little petal of a flower saying you can also do A. But at some stage, if you say, well, no, actually, you can do A only if it was preceded by B, all these loops are removed, and then you start adding new arcs to states, things you can do and you cannot do.
Intuitively, if you add constraints over tasks that you have not previously constrained, it will grow.
Yeah.
If you add constraints over tasks that are already constrained, it most likely will shrink it. Yeah.
Maybe, but it's not always. This is cool, right? So, good. So this is problem number 1. Problem number 2 is, we said when we add constraints, the order doesn't matter, but when we remove them, well, the order might matter. So we identified a few kind of sorting strategies, like the position of the template in the hierarchy. So the strictest first and the loosest later on. Or the confidence and support of the constraints per the log. Higher support first, lower support later on. Also starting from activities that have more constraints around them, either as an activation or a target. So these are all strategies, but we don't have a favorite solution. Again, when we say watch out, I think you already caught that by reading papers. There is a moment in which our solution is customizable. The user can determine what's their favorite strategy. Means we have absolutely had no clue what's the best strategy, so we defer the responsibility to the user. That's your trick, right? Fantastic. It's like thresholds. What is the best threshold? Well, it's customizable. It's not a bug, it's a feature. So, and then here it's represented by this obscene writing. So essentially, we can claim that the technique is, well, linear or at most quadratic in the number of constraints n. If we take this guy as a constant, what is this guy which is strange with the circle with an A and the T, what the heck? That is the automaton product operation. So if we take it as if it was given by an oracle, it would be linear or quadratic. But this guy can go big time, exp time, right? So, and it's uncontrollable because we don't know what's going to happen there. So it's effective, but it's really unstable. So it could be that sometimes it works in a snap, sometimes it just gets stuck, sometimes you go to Stack Overflow. We don't know. It's an untamed beast yet. So please, if you have new techniques stemming from whatever area you're into, please contribute. It's an open problem. All right. Then we have started looking for a new investigation. In this case, we talk about the unsatisfiable core. That's not a problem, right? So we said we are certain at the end of our parsing, we are sure that at the end of our parsing, if there's a conflict, we'll detect it immediately because there is the nothing automaton popping up, right? So if we remove the constraints causing it, we're sure that in the end, the model is conflict-free, right? It's sound. It's provable. But thanks to the observation of Marcos, we also know that it's not necessarily the minimum core of conflicting constraints. Let me show you with an example. We have this list of constraints, and altogether they are in conflict. What can I do? Where is my conflict? And then my suggestion would be, well, take them all away. Done. Conflict resolved. Right? Or just keep one constraint. Yeah, but are all the others, conflicting? Well, I don't know. But if you keep just this one, it works. Right? So you see the point. We want to minimize the pocket of inconsistency. UC, unsatisfiable cores. Now, we have tried 4 different techniques. The first one was like reduce it. There were some techniques for LTL, the infinite time LTL. So the one for which Homer Simpson would be happily running back and forth in the nuclear plant forever. We adapted also LTLF native techniques. But in the end, what's bad is that we didn't have one silver bullet. Even though trying different techniques, of course adapting them, but still, it depends on the kind of data we have at hand. So this is a called cactus plot, literally. It's like a cactus, right? So essentially, it should be read like as follows. So these where is it? These guys are different techniques. The green one is the virtual best. Virtual best means that the number of solved instances requires it tends to grow slowly with respect to the CPU time. Right? So if you grow like this way, cumulatively, it means like you don't scale well, right? So at first sight, okay, maybe you can't read what this line is about, but this looks like the blue tool is the best one. Why then we have this sudden peak and the green line tends to detach from it? If it was the best one, the virtual best and that technique should be basically matching. The fact that they don't means that there are certain situations in which one algorithm is better than the others, which again, we can claim the following. But then we can claim the following. We leave to the user the freedom to choose the best algorithm they like. Yeah, come on, right? Just because we can't really guess. Also, this is a nice, what's that? A nice plot. Now I forgot the name of it. Not the Kinsey. Sankey, thank you. Great. Sankey diagram. This is nice because basically it allows us to compare 2 different variants of performance. So we basically took the performance in terms of timing versus the performance in terms of the size of the unsatisfiable core, the cardinality, right? Because we want to achieve both. We want to be fast and we want to find the minimal core of unsatisfiability, so as to get rid of it. Now, looks like this guy gets the lion's share for the timing, but it's not anymore like that if we look at the cardinality, right? So it tends to be quite cool. So in the end, we found out that if there are few propositional symbols, namely activities, okay, involved in the constraints, but many nested temporal operators, which means like, you know, eventually next, always next, eventually implies eventually, right? So few actions, large templates, then one tool tends to work best. Instead, if there are, where is it? Oh, sorry. My bad. These two shouldn't be the same, right? Instead, if there are, say, the opposite, many actions but simple rules, then the red line, the Alt F, just goes great, which is basically all the other cases, right? So depending on the way in which you're specifying your process, your rules, if the rules are complex but with fewer actions, choose this. If your rules are simple but there are many actions possible, then choose that one, right? So there is no one solution for all.
Can I ask you a question?
Please.
What about simplicity? I mean, there are some rules that are simpler to understand than others.
I missed a slide about that. We ran a test, a guided experiment with users, yeah, with an A/B test, A/B groups, etc. And so we tried the following. We are showing just the textual description of a process and the description in terms of constraints, and also both. Now, what happens is that whenever we talk about constraints, the performance of a task to describe the process from the users decreases. Like, so this basically, it's a great hook for the next slides, but just saying, so simplicity is hard for two reasons. First off, quantitatively, of course, the more the rules, the harder it is to bear them all together. I mean, I don't know, do you have any relatives or friends who are lawyers? You do, right? Some of us do. So good lawyers have an impressively good memory, and they know exactly which law applies to this case so as to get either, you know, their client out of jail or out of trouble, or the other way around. Yeah? So what are they doing there? Basically, they have a very large index of rules in their head and know exactly where to pinpoint the case that applies. Is that easy? If it was, they wouldn't be successful lawyers, and we would all be lawyers, right? So number is an issue, first off. Second thing is also the complexity of the rules. If the rule is very complex, then it's harder to be borne in mind. We can't bear it in mind easily with the others. What I'm saying is, if I express a rule such as, if you do A now, next do B, that tends to be simpler than saying, if you do A now, eventually you'll do B, but between A and B you can't repeat A. See the point? So even the nature of the rule, there is an inherent difficulty. So we still lack a study. So please, you're all welcome to study a measure for the simplicity of declarative specifications. Don't have to be declared. Could be anything, but just as long as we have some guidelines, because we don't have it yet, right? As far as I'm aware. I mean, if you know anyone, I mean, lucky this is not being recorded, right? No. And so I can't be finger point like, actually I did that. My master student did that in the 70s, but I don't know. I really don't know. I'm not aware of it. Okay? So, but thanks a lot for this great hook. It's just fantastic. It's good that you guys are sitting one next to another, because basically they're kind of, you know, good spoilers for the next slides. No, seriously. I'm almost done, okay? So we're getting closer to lunch, I think. What time is it? Why am I desperately too early?
Fine. We have 1 hour, but we can...
Oh, wow, okay.
But I can ask you questions for 1 hour.
Indeed. This is great. Okay, so first off, the things we have been talking about are implemented into open source, freely available tools. So with and without a GUI, okay? So depending on whether you want to go the SKU dry away or for users. today in the afternoon, we'll have a look at both. Okay, the tutorial will be more guided towards the hard one with the without GUI, so we do it together. Whereas the tutorial for the GUI version is basically, well, read the document, try it yourself.
Which one are we going to use from the three of them? Or?
Manifold, the first one. Yeah. Janus is a fork, literally, of Manifold that does other things, but, well, and LTLFUC, it can be pronounced differently, but it would be a bit massive, is instead the one that is just specialized in finding the unsatisfiable cause with the 4 different tools and all that. RUM instead, RUM, is the one with the graphical GUI. But inside RUM, these and other tools are running. So it's a kind of wrapper of different techniques. So there are a lot of open challenges. Yeah. So for instance, we have started talking about just actions. But again, let me try with an example here. I'm going a bit slow because then we can reason together and we can save time. So anyway, we have a rule. Whenever a loan is requested, it is always granted afterwards. The confidence of this is like about 50%. So what would you do then? Well, it's below any possible threshold, so just discard the rule. If instead we said whenever a loan is requested and the credit score is above 150, it is always granted. Well, this is interesting, and you wouldn't discard it, right? Confidence is 100% in that case. What's the difference? In the first case, we didn't care about the information artifacts on top of it, the credit score, right? Shall I repeat that part? Okay, let me try again. If you request for a loan, you get the grant. Confidence 50%. It's below the threshold, you just discard it because it's not interesting. The same rule, if request, then grant, is addition with the following. If request with credit score, you see it's not an action, it's a data piece higher than under 50, then it's always granted. Well, then you keep this one, right? It's interesting. What's the difference? The data score. So looking at just one perspective, I think we talked about that twice, both on Tuesday and on Wednesday. Because with Danielle, we show that there are different perspective process analysis, also for variability. And with Felix, we also saw that this applies also in the case of process architectures. You have views on a software architecture or process architecture. Same story here. If we miss the view about data, then we'll be missing a lot of interesting information big time. But nowadays, we're still struggling to find algorithms that can both take into account, can take into account multiple views. For the imperative side, they're well established. For the declarative side, it's a bit less. There is a work from Volodymyr Leno and others who actually apply these techniques for one particular case of correlation between activations and targets. But yeah, the challenge is open. Another thing is, not all the traces in the event log report unhappy scenarios, right? So a typical instance of our analysis could be, tell me what are the behavioral rules that determine when a trace, a process run goes pear-shaped, goes badly. Well, in that case, we have to start discriminating, labeling traces, the good old machine learning way. You label the traces as positive, negative, positive, negative, positive, positive, negative, and then you have to find the patterns that discriminate the two. Again, you can see that as a sort of variant, but in fact, it's a bit more than that. We're kind of enhancing our discovery algorithms with the capability of discriminating between the things that bring you to the success of your strategic goal and those which don't. Yeah? Again, challenge is open. It's also nice. When I was peeking into email data, which again is something that is heavily against and is sort of GDPR, etc. But anyway, you can say that in that text, if you talk about an activity, it means you have done that activity, right? Even determining what the activity is about is hard. In that case, turning the email into an event log is not really appropriate, because you can't just say the event happened. You can say, well, the event probably happened with this score. I'm not aware yet of any algorithm that can try and determine behavior rules out of event logs that have events that are probabilistic. So the event didn't happen, it happened maybe with a perhaps 70% chances, right? Also, because if we start doing that, we abandon one of the mantras of event logs. In event logs, we have a total straight order. Nope. Because if an event happens or not, it means that the next one could be, scaling up in the sequence, which is, again, another interesting twist. So, any ideas are very welcome. So to come in finally to the kind of vision in the long run. So this is going a bit, a bit formal. So does anyone know what this symbol means? This. It's not table 90 degrees reversed, not pi. This means modals, okay? So just modals. Models like model, process model, yes. That's the cool part. You may have noticed that throughout the entire talk today, we always talked about specifications, declarative specifications. We never said declarative model. Why? Let's put it this way. If we set the rules of the game, like the logistics domain, law, healthcare, then we say, well, your organization can run processes given this normative framework. But then the way in which you run your process is your own idea, right? Now, what's cool there is that this symbol here represents exactly this. So your model models a specification. Models in AI and formal methods are interpretation of your word that satisfy a given theory, set of rules, set of formulae. There we go. So the idea would be, in fact, how about, so in this case, for instance, I don't know if you are familiar with workflow net. This is actually a Patronet more than workflow net. And basically, this goes like that. So write your paper, submit the abstract, submit the paper, receive the confirmation email, then you can review the paper 3 times, accept the paper, or reject the paper, and you're done. Linear. Well, it's a bit of a snaky version, but it's linear. I know you can't read that. That's why I read it out loud. Okay? This is one possible execution, set of executions condensed in a process model that actually satisfies, i.e. models, these rules. But it's not the only one. Remember, there was like a large automaton. So the idea could be this long-term vision. Let algorithms, rather than give you exactly the process model as it was by the data, try to be a bit looser, yeah, and give the facts that you can extract from the event log. They can have a high confidence, a high support, they tend to fit this model. So these are the kind of fixed rules. Then the imperative model is the soft knowledge of your organization. Given the rules, they are facts. The way in which you kind of, get your route through this wrench is your choice. So we can use automated discovery from data to derive the non-negotiable rules, and then let reasoning, planning, and enhancement with human knowledge find out what is a possible strategy, the most fitting one that actually the system uses and you use to drive the process through this kind of, borders. So basically this, however, it's a bit tougher because, this automated discovery from data can be something we can do in our laboratories, yeah, computer laboratories, or machine gun. I don't remember what's a fancy name for it. Anyway, that one. Great, thanks. Whereas instead, if you want to go the full throttle, then in that case we have to use intuitive and explainable AI, because we can't just say, okay, this is the process. Why? We have to explain that. Keep the human in the loop, and possibly using generative AI to generate solutions on the go. So, with this, for now I'm done. I understand I'm really much in advance. I didn't get this. I didn't suspect this, but maybe because it's just too smart. So we didn't have to repeat things twice. Thanks. Right. So any questions, feedback, comments, insults, I'm here. Yeah? So thanks a lot. Yeah, sorry. Any remarks?
Y preguntas que tengan. Crea,
Yes, please.
When I send work, or I work with somebody with imperative models, PMN and stuff, they ask me to do it in declarative models. When I send something in declarative, they ask me about imperative models.
Yeah.
When I should use one, when I should use the other, which one is better, which one is worse.
Okay, that's a fantastic question. I don't have a solution for it. I can, of course, but maybe we can discuss about some intermediate advancements, okay? So, first off, the expressiveness of declarative approaches, which we have seen here, is strictly less than that of imperative, right? And a fantastic example, if you don't want to talk about Homer Simpson and all that, is the switch behavior. So, switch means you toggle and toggle twice. So if you switch the light on, switch it off. Switch, switch. So if switch, later switch. But if switch, then later switch. Then let's switch, 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 switch. So this kind of LTLF cannot discriminate the toggle behavior. So it's very, very simple under that perspective. Clearly, it has its own complications. But at least it has the opportunity to single out portions of behavior. Right, so this if-then is also interesting because maybe if the immune system was marked as excellent here, then the therapy can be harder at the end of the process. Now, to find this kind of long-term dependency in a Petri net, well, might be not so intuitive. Maybe in a Petri net it does, because you have these particular places that you can connect with which you can connect the two. But let's say BPMN, well, then in that case you have to check the DMN tables we saw in a few days ago and also yesterday, see if they compare, etc. Instead, the declarative approach would just say it immediately, like if you execute this activity because you have an excellent immune system, then later on, or the other way around, if it's not excellent, then you can't go there, etc. But to have the full view, well, no, declarative approaches don't really work. Because the full view is given by an example. There has been a very cool thesis, PhD thesis by Sebastian Uchitel, and this guy is into software engineering, and had this idea. So clearly they weren't using any declare or anything like that, but anyway, they were basically tracing some expected fragments of behavior by the system, basically user scenarios on steroids, and then composing them. That all the scenarios together would make a story, but it's hard to keep track of all the evolutions. So then they would condense this and start running the simulation of the process. By the way, don't miss tomorrow's lecture, which will be exactly about this. You would simulate the execution of your process, trying to get the edgy situations about things that were not clearly depicted in scenarios, but could still happen. Then it would propose it to the stakeholders and ask, do you like this execution? Yes, no. If no, then they would basically come back to the scenarios and refine it by avoiding that, truncating it. We'd like to work on that too, but again, it requires the human intervention. Without a domain expert, it's hard to realize if a dodgy situation is good or not. So anyway, describing full-blown processes via declarative manners is very tough. really. Instead, showing examples how the process could unfold tends to be easier to pick. But then again, it's sort of, re-entrant thing. So we have now a system to go from imperative to declarative, from declarative to imperative, although the issue is that the things that come out of it is completely misunderstandable. We have also, if you go for Patronets, they have repeated tasks, hidden final states, all the worst. But still, it's there, so we can also refine it. Thank you. Then there was a question.
What about a mix between imperative models and declarative models?
So the hybrid models are great. I love them, especially because they are sort of, a mind trick. It's you look at them and you feel like, okay, I got a hunch about what it is. You don't, because there is a big difference also in terms of execution. If we look at this particular model here, if you see a unicorn, you will publish a paper, right? So the thing is that it doesn't tell you exactly where you can't point the finger and say, I'm here, and the next action it will be this or that. Basically, they tend to hold together for the whole time. So at any instant in time, you could still submit an abstract. All of a sudden, just because. You have nothing preventing you from doing this. So even that, let's put it simply. Am I still visible here? Kind of. All right. Sorry for the snake-like process, but I hope you'll forgive me for that. Yeah. AB. What's the sequence? AB. Then I put a nice feature here, and I say, well, actually, every time I meet an A, I should also meet a B later on. So you create a loop. Or worse, sorry, the thing is that when we add things up, they tend to potentially stumble upon each other's feet. So one idea that we had because we also did some analysis on conformance checking in the presence of hybrid models, and I was cursed with the objective of creating the running example. I mean, running example, I don't know if you like it, it's terrible. You have to find something that's clear enough to be caught at first sight, but also complex enough to be told throughout the entire story, right? So what we saw is that typically, if you want to have an imperative side and a declarative side, it's a good idea to not let the two speak about the same activities. So it's a guideline. Again, the challenge is open. If you want to conduct a study about this, please do so. We need that. We have 7 processes PMG, and we saw it yesterday and the day before yesterday. So 7 PMG drives the way in which we describe our systems, right? But that's all for imperative stuff. There is no 7 PMG for declarative things, or let alone hybrid. Nothing like that. So one idea was depict a sunny day scenario here with imperative one. Why is that? Because the sunny day scenario, in the end, tends to be a bit simpler to follow. When there are exceptions, then go, or kind of edgy situations, so things that basically don't enter here. So the all that, let's go declarative. Also because typically these exceptions can happen at any moment in time. For instance, we have seen at some stage a particular feature it's not visible, right? So can I copy and paste? All right. It's okay. I mean, this is also something I don't particularly trust. Sorry. Yeah. Well, inside we have a B. right? Timer event. If there's a timer event, then you'd go for C and close. Close and terminate. Just saying. This is declarative. Do they you like, but if something happens, it could be a timer, or I don't know, you catch a signal. Signal comes up, then, oh sorry, signal should be black. No, white, you receive. The signal event occurs at any point in time. So if declarative, then go there. So while a tree could be, let's consider actually BPMN already is declarative, hybrid inherently. It's quite nice. Difference is that in this case we can isolate the moment in which the rule applies. Here we know that this catching intermediate catching event is here. If it occurs before or after, well, okay, there are not many other activities around it, but let's say D. If it occurs here, you don't capture it, so you don't care. Declare instead is basically spread throughout the whole execution, so you can't really limit its validity. This opens the door to new semantics, new expressions of semantics, like for making to make the declarative approach composable, which currently isn't. So it's cool, but again, we lack a bit of acquaintancy with these instruments to come up with some mature theory about it. So again, yeah, cool. Thanks a lot.
Okay, so we're finished.
Woohoo!